The subject of this lab is to use Newton's method to find zeros of functions. Remember, a function is going to equal 0 where it crosses the x-axis. In this particular case, that would be occurring right here. According to Newton's method, you would take some approximation for your 0 or your root of your function, and notice, this approximation is pretty far away, but it's a starting point. And you draw the tangent line through that point. And notice where the tangent hits the x-axis is now closer to that root or 0 of the function. So now we let this x value select our next point on the function, put it here. I draw the tangent through that point, and notice where this tangent hits the x-axis is even closer to my actual root. So what Newton found is that by doing this method repeatedly, you can find the value of this root with a fair amount of accuracy. Here's the formula. Let's see where it came from. We're going to begin with the point slope formula. We want to know, where does the tangent hit the x-axis? Okay, well, the point that we have on the function right here is the point x sub n, and its output, rather than calling it y, I'm going to call it f of x sub n. So that's what you see here, and I'm going to substitute that for my x1 and my y1 in my point slope formula. The second bit of information you need, of course, is the slope, and as you can see right here, we're being reminded the slope of a tangent line is the value of the derivative at that point. So the first step in deriving Newton's formula is to substitute those values. We want to locate where the tangent is going to hit the x-axis. Any point on the x-axis, which is what our root also is, always has a y coordinate of 0. So I'm going to substitute 0 in for y. Now, if I can just solve this equation for this x, that would be the root. I'm going to simplify. If I do 0 take away this quantity, that's going to be the same as just negative f of x sub n. And on the right, I'm going to apply the distributive property and distribute my slope, my derivative, to both parts of the binomial, giving me f prime of x sub n times x minus f prime of x sub n times x sub n. I want to get x by itself. I'll begin by moving this term to the other side using the opposite operation. So if I add it over to the other side, it will become positive, and I'm going to put it out front. So I now have f prime x sub n times x sub n minus f of x sub n equals f prime x sub n times x. And to continue getting x by itself, I want to get rid of this f prime x sub n. I will divide each term by that. Now I simplify each of these fractions. There's a common factor of f prime of x sub n in the numerator and denominator here, so those will cancel. Nothing cancels out of the middle fraction, but over on the right-hand side, I again have some nice cancellation that will occur. What is left behind would be x sub n minus f of x sub n divided by f prime of x sub n, can't cancel those, one's a derivative, one's not, equals x. And this is precisely the Newton's formula that you see up here, with one change. He then labels the x that we solved for as the x sub n plus 1, as the latest x approximation for the root. So if I put that little n plus 1 on here, this is Newton's formula.